are publishing all these videos. We will share the video, or we will share the link in the chat box after some time. You can download or you can see the videos on a later stage. Now, to start the program, Dr. R Nagabhushana, all of you knows very well. He is, I would say, the most eminent person in India for lightning protection. He is the formerly professor and chairman of the High Voltage Engineering Department in Indian Institute of Science, Bengaluru, and presently he is the Professor Emeritus of MS Ramaiah Institute of Technology in Bengaluru. And regarding his experience, last more than 50 years, he is in the field of lightning, and he has designed the lightning testing facility for DRDO, the Aeronautical Development Agency, where our India's most important fighter aircraft, the light combat aircraft, and the other, helicopters of the defense are tested against lightning. So to start the program, I would like to invite Professor R Nagabhushana. Sir, over to you, sir. You can please start.
Thank you very much, Mr. Gopakumar. Thank you very much for the nice introduction. I'm really very happy to be with all of you. Let me wish good morning to every one of the participants and welcome them for the this webinar. Just to recall,
share the screen, sir. Sorry to interrupt you. You have to share the screen.
Yeah. Okay. Good morning to all of you once again. Good morning to all of you once again. If I just recall, what we discussed in the first webinar was essentially the atmospheric electricity, in particular reference to lightning. These counterparts in the upper atmosphere, namely blue jets, yellows, sprites, and tendrils like that. Subsequently, we discussed the main item of the all set of webinars, lightning. How the cloud gets electrified in a very, very elementary way, because there are so many theories, but none of them are really possible. None of them are capable of explaining the full phenomena of electrification at all. Even today, after more than a century and a half work, it has not been possible. Only thing anybody can say is that there are a multiplicity of phenomena which contribute to the electrification of the clouds. And lightning, majority of the lightning is transfer negative charge to ground and positive charge to the ionosphere, and this process helps the global capacitor consisting of the lower ionosphere and the earth at a constant potential of nearly constant potential of 250 kilovolts to 300 kilovolts. That's the basic phenomena of lightning. And we studied also, we very briefly went through the characteristics of the lightning strokes, current ranging from 2-3 kiloamperes at the lowest, going up to 200 kiloamperes for negative strokes. The highest recorded, if I remember right, is about 212 kiloamperes. But for positive strokes, which are very rare, the highest current reached is about 360 kiloamperes. That's a very rare phenomena, and it's not easy to catch that also. This is about the first webinar. In the second webinar, because of the lightning strike to tall objects like trees, poles, even tall buildings, it can create a lot of hazards. Even if people are in the open area, they are subject to the same dangers because of the current hitting the tall objects, flowing in the ground over long distances. Therefore, either by contact with the tall object where the lightning has struck, or in the close proximity because of the potentials developed along the ground near the tall object, there are many fatalities involved. It is reported that in India alone, nearly 2,000 to 3,000 fatalities occur every year, even though unfortunately, the recording is not very formal. We get the numbers mostly from papers and then TV channels. I think, I hope that it will get formalized very soon, so that they know the exact number who are injured also. Till now, injuries have never been reported to my very best knowledge. Injuries can be very severe. In fact, in the developed countries where they have got extensive records, it is known that injuries is nearly 10 times the number of fatalities. That means if you think of America, with all the developments, education, till about 35 to 40 deaths occur every year, and the injuries are 350 to 400. This was again 10 times these numbers about 10 years ago when the education was not still very effective. So in India, if you think of 2,000 to 3,000 fatalities, you can imagine the number of injuries. It may not be 10 times. Probably people are more sensitive to electric shock. They might be dying more easily than getting injured. That's not known. Unfortunately, as I told earlier, this data is not formally and properly recorded. I wish it is done in the future. It is not an easy task, but it's worth doing it because the knowledge will be properly based. And the types of injuries, many photographs of various types of injuries were also shown in the last webinar. It was really very useful to share the injuries. If the people see the types of injuries, then people will get a little alarmed and they are likely to take the precautions. That means mainly avoiding contacts with the tall objects during thunderstorm weather, being in the proximity of tall objects during thunderstorm weather. As the common saying goes, when thunder roars, go indoors. You'll see today that indoors also can be a little problematic, quite problematic. Contact with the outer walls, electric wiring, etc. can be hazardous. I will show one or two photographs of that also today. So in today's webinar, we'll mainly discuss with the buildings, because in the last seminar we dealt with the human hazards and animals also. We saw that animals are more susceptible because they move in groups. Now, the today's seminar, as I told you, deals with mainly hazards and protection of buildings. Again, what are the types of damages? It may be a structural damage to the concrete or to the wooden structure, and possibly fire hazards are possible, particularly if they are wooden structures, particularly damages to interior of buildings like the electrical wiring and devices. Of course, humans also inside, as I told you, if they come into contact with the outer walls or the electrical part of it, there's the electrical lighting wiring or telephone cardless phones, things like that, it can be quite hazardous. We will see some of the hazards by photographs. Figure 1A shows that a whole parapet of a building has got shattered because of the lighting incidents. Now the next one, 1B, here shows the extensive damage that can occur to the top of a building if it's not properly protected. It's very, very extensive. Almost the whole roof has disappeared because of this. Of course, the type of damage that would have occurred inside, one can really imagine by looking at the damage that is seen in the photograph. Really, it can be really very bad. The 1C figure shows a fire caused by lightning. You can see the extent. It's really amazing how wide and how dangerous it can be. It's really very, very, very dangerous, obviously. In figure 1D, we have shown a number of cases where lightning has damaged the electricals inside a building. It can be the switch contact, or it can be the washing machine. It can be anything like that. And it can also affect the humans in contact, as I told you earlier. Let me see, I think the next photograph. You see here, close-up of the damage to the switch mounted on the wall. And then in the last 1F, a person has suffered the shock due to contact with the wall or the electrical wiring. The details are not available, but it's really very, very shocking. Staying indoors, suffering lightning injury like this. I hope it was not a fatal case. Details are not available, but what it tells us is that we have to follow some very simple, easily followable methods to avoid all these dangers to not only electricals, but also to humans. Now, looking at the protection part of it, the backbone of protection is the tall buildings must be provided with rods, what are called lightning rods, which was initially improvised by Benjamin Franklin. They were therefore called Franklin rods, and then normally they are known as lightning rods. Also, both names are very commonly used. They mean the same thing. And then the Franklin rods or the lightning rods, the current has to flow down So we have to provide a set of conductors which are named aptly as down conductors, and these conductors must be earthed so that the fundamental process of current flowing into the earth from the cloud is completed. So this is known as the earthing system. We'll be covering only the principles of the whole lot, not going into the details, because the details of the down conductors and earthing particularly are can be quite involved depending upon the configuration of the building and other many other possible complications like the structural discontinuities and things like that. Then the rods that are to be used are to be much taller than all the objects intended to be protected, so that becomes the preferred point of lightning stroke attachment. Now, the top tip of the rods, when the leaders approach, lightning leaders approach, they can create very high fields at the tips of these rods. Streamers develop. Streamers are local discharges, which is caused by ionization due to the high field locally there. And then, therefore, because a lot of ionization is there and there's an extended path above the tip of the electrode, extension means maybe few centimeters or few tens of centimeters at the most, that becomes a preferred attachment point for the leader. Therefore, this top rod, the top tip of the rod and rod as a whole is known as the air terminal. Now, once the leader contacts the top tip of the air terminal, then the return current starts flowing from this point. We get the return stroke. The current in the return stroke is the main current. That's the damaging part of it, a damaging part of lightning. I must emphasize here again, the voltage of the cloud initiates the lightning, or in other words, provides the means of breaking down the air and allowing the path to develop through which the current flows. It is always the current which is the damaging factor. Current is the damaging factor. It's not always the voltage. The voltage drives the current, and that's how the current flows, and this current causes all the damages. So now the proper current flow path from air terminal to ground, that's known as the down conductor, must be provided. So apart from the rod, there must be a down conductor, and then the down conductor must be properly connected to earth. Properly, what we mean, we will see a little later. Now, extensive research and field experience for over a century have led to very detailed standards, for which there may be no mathematical explanations all the time, but we have to depend upon field experience and research based on field experience, which have led to these detailed standards. For actual incorporation, reference to adherence to the above standards, namely IEC, International Electrotechnical Commission 62305, and its counterpart in India, Bureau of Indian Standards 62305. They give very detailed information. There are three parts, probably 4 parts. They give extremely detailed, very thoroughly detailed instructions for incorporating all these air terminals, down conductors, and earthing systems. Now, so this is the figure taken from IEC 62305, which has been cited earlier. There are 4 curves in this, 1, 2, 3, 4. They correspond to the levels of protection. You can say curve 1 corresponds to a current of 200 kiloamperes, because this can cause the maximum damage to internals. Therefore, the protective angle must be short. And then for taller buildings, and where the current level requirement is a little low, that means provide significant protection systems are provided. So I'm not bothered about the lower current levels, but I'm bothered about the higher current levels. Therefore, I can have larger protective angles, about which I will talk just now presently. Now, as I mentioned to you, lightning protection levels L1 to L4 are mentioned in the figure. L1 to L4. Sorry, the table is missing here. Okay, it doesn't matter. The current levels corresponding to these systems are shown here. Now, dimensions of the conductors, characteristics of such protective devices like spark gaps, low discharge tubes, varistors are also involved. The specifications technical requirements, how they are met. We will not be discussing this in the present talk because that itself can be a huge course, not merely 1 or 2 or 3 webinars, but a huge course. Characteristics of each of these devices can require more than 1 webinar for understanding it fully. Now let's come to a little more discussion on the lightning rod or the flank ring rod. Now, Benjamin Franklin, in his famous kite experiment in 1752, followed it by using a tall rod mounted on top of his building. First one, of course, was on his own residential building, which used to attract lightning to itself, and that was provided with a down conductor, even though that name was not yet commonly used at that time. It was brought down and then earthed. This rod or tube obviously has to be much taller than all the objects that it is supposed to protect. What's the protected area? This is the big question. What's the protected area? Suppose I put a rod which is about 100 feet high. How much can it protect? Can it protect a huge area, or it's only a small area? It's a very big question. For this, we have got a principle called protective angle method for appreciating how this rod works. Now, here we have got in this figure a lightning rod or Franklin rod. It's a metallic rod or tube, and then we have got a semi-conical volume covered by this cone. I have shown in dotted lines. So the area with radius r at the bottom is the area. There's this rather circular area with r as radius is the area which is protected from direct strokes. The lightning directly hits the rod tip, and therefore it will not hit this area. This area at the ground level. So this is a protection from direct strokes. As we will see a little later, other dangers like contact and ground current potentials can be very substantial. That's very dangerous, but is really worth repeating. Lightning rods of this kind, this particular pole protection against direct strokes. It attracts the lightning to itself, then conveys it to ground through the down conductor system and the earthing system. Now, the angle theta, originally purely intuitive. That's why we call it geometry. It's only a cone of some angle theta at the vertex. It's purely intuitive, and it was highly debated at one time. It started from 15 degrees to 60 degrees, a huge range. After considerable field experience for many, many decades, it stabilized at 30 degrees. So for many decades, it was thought that if you provide a rod, the area with 30 degrees semi-conical angle at the tip, the circular area at the bottom is protected from direct strokes. That is the basic principle of the geometric method. When height approached 100 feet, it was found in practice that this did not work efficiently. 30 degrees was too high. The protection area was not equivalent to the circular area, which corresponded to 30 degrees semi-conical. Therefore, the protective angle theta of figure 2 was reduced to 20 degrees. So this depends purely on the geometry. Therefore, it's known as the geometrical method. The table 2, figure 1, which I showed just now, gives detailed currently recommended values of theta depending on the height of the rod. For large height, h greater than 100 feet, it is recommended that rolling sphere technique is to be used. We'll be discussing presently. I will go through. We have already stated these things. Now we will come to this called electro-geometric method, which involves both a geometry and an electrical parameter, essentially the current in the lightning. We'll see that the prospective peak current in the lightning stroke is related to the production scheme through what's called the striking distance, appropriate for heights greater than 100 feet. If the height is less than 100 feet, we don't have to worry too much about this electrogeometric method. The simple geometric method we discussed till now, the semi-conical angle of some angle theta, is quite valid. Now, what's the basic principle of this electrogeometric method? Now, assume that the forward stroke of the lightning which is not visible to the naked eye. Please remember, it's not visible to the naked eye. I have assumed that it has come down to the point P naught. P naught is a come down step by step. I have shown only one branch. There can be many branches, but what the important thing is that reach down to point P naught. There is an object on the ground where streamers also occur because the electric field induced by the potential of the leader which has come to the point P naught. Now, will it strike there or will it not? That depends upon the electric field at the tip of the leader, the intensity of the streamer, the distance, most importantly, the distance between the two. We'll see a little more when we go further now. Now, the length of the next step, supposing the leader has come to the point P naught as shown in the previous figure, the next step was shown to be related to the prospective current I in the stroke as the relationship given here. Yes, the next step distance is equal to a constant K multiplied by the current I raised to the power of N. Now, remember, lightning has got many statistical parameters. That means we cannot have one constant for K. Similarly, we cannot have one constant for N. For strokes which have occurred in some area, for various currents in that region, we may find, say, different values of K and N. Like that, the constant estimated variously globally, K has a range of 4 to 10. It is a little surprising, is it not? Very surprising, 4 to 10, 1 to 2.5 times. And I is the prospective current in the stroke. Remember, the current in the leader of the stroke is very small, maybe the order of 1 to 2 kiloamperes, nothing more than that. But the prospective current, suppose it strikes the ground, what's the likely current it will reach? That's the prospective current. So N is a constant, variously estimated in the range of 0.4 to 1.1, almost 1 to 3. K, 4 to 10. I is a prospective current, which can vary from 2-3 kiloamperes right up to 200 kiloamperes for negative strokes. N is a constant, that's the power. In this equation, I have shown equation 1. It varies in the range of 0.4 to 1.1. Please note again the strongly statistical nature. So if you find that a given aerial system, etc., did not give 100% production, it did give you, let me say, as an example, for a few years, there was no problem at all. Suddenly 1 year, there is a damage caused, even though the aerial production system has been provided. We cannot say the system is faulty design, because the severely statistical nature of lightning is reflected in this equation S equal to K I to the power of N. Because of the statistical nature, it is possible that sometimes, relatively rare times, there can be failure of the production system. Now, a commonly used value for the constants K and N are 10 and 0.6 respectively. So the equation 1 becomes S equal to 10 times I to the power of 0.6. So S is the next step length of the leader from the point P naught. I is the prospective peak current in the stroke, and then constants are 10 and 0.6. The power is 0.6. The constant K is 10. So you will see that the step distance is a parameter that we are going to use for the design. I is the prospective current. So these two are related. Therefore, apart from the geometry, yes, distance, the current is also involved. So it's now a electro geometric method. Electric current I is involved. The geometry, the distance is involved. Therefore, it's an electro geometric method. Now, table 1 here shows, okay, it will not be blocking. That does not, okay. This table 1 shows so-called next step lengths, values of S for a few values of I, typical ranges. Suppose you think of the lowest current, 99% probability current is 5 kiloamperes. 2 kiloamperes has also been seen, 2 to 3 kiloamperes has also been seen, but the probability is extremely small. So as a round figure, 5 Ka has been considered here. Then 10, 20, 50, 100 and 200 kiloamperes have been considered. And from the equation, I equal to 10 I to the power of 0.6. If for Ka, 5 Ka, the rounded off value of S is 26 meters. For 10 Ka, it is 40 meters. For 100 Ka, it is 158 meters. For the highest current in the negative stroke, the striking distance is of the order of, or the next step length is of the order of 240 meters. So this gives us some lead as to how to look at the whole phenomena, which we'll be doing right now. As I said, the implications of them are quite interesting and useful. Values of S are commonly referred to as striking distances for the respective currents. I'll repeat, the values of S are commonly referred to as the striking distances for the respective currents. Where did it go? Now let us see how we can apply it in practice for arriving at a production system. Now in this figure, they are shown two buildings, B1 and B2. Obviously, B1 is almost twice or even slightly more than B2. The lightning leader has approached down to point P0. If I put my hand, they can be seen there. Okay. P0 here. See, it has come down to that. The next distance we can calculate using the formula for step distance. So now, for a current IS, let me say, it can reach P1 if the striking distance is equal to D1 or more. Supposing the striking distance is not equal to D1, I'll repeat it. The leader stroke has come, forward stroke, leader of the forward stroke has come down to point P0. Because of its current in the stroke, the striking distance is not equal to D1, but is less. So what it will try to do is, it will not go in this direction. It may go in any direction to a distance smaller than D1. I have considered this distance and then another distance like that. Because remember, the most important point is the leader will not travel in a straight line. I will repeat, the leader will not travel in a straight line. Now, what happens is that at the leader tip, the electric field strength has got a good value. It's capable of proceeding further. But in which direction does it proceed is the important point we have to answer. Now, if you consider the area all round, the electric strength of the air in that spherical volume is not the same. Therefore, this leader will develop further in the direction in which the electrical strength of the air is the weakest. It will cause a breakdown of that air in that particular path, and then it will travel like this. So again, it has to take the next step. It will come down like this, again like this. Now it has become far from point P1, so it cannot hit the building P1 at all. So now let me repeat, if the current is high, if the striking distance is D1 or more, then the stroke will go directly to point P1. If the current is less than the striking distance corresponding to D1, then it will take any direction, not necessarily in this, even though I have shown it towards B2, it may be in any direction. Here I have considered towards B2. So therefore, it travels towards B2, assuming that this electrical strength of the air in that direction is the weakest. It will start developing in that direction, take another step in the weakest direction. So now we see this is quite different from the previous distance. Comes here, like this. Finally, it will come to P2, which is one of the corners of the building 2. So now the important moral we have to learn from this is, for a current which is smaller than corresponding to the distance D1, it will not hit the taller building B1, it will hit the shorter building B2. Now in the last webinar, there were two questions, which was like this. In one case, they said, I have seen lightning stroke occurring to a shorter building, which was almost next to a taller building. Why? The answer is this. So the current in the lightning stroke was lesser than what was necessary to cause an attachment to the taller building, then it will go towards the shorter building. So this answers that question. Secondly, the other question was, probably I think it was a gentleman from the electric power industry. He said that, well, he asked that there were two transmission line towers. One was taller than the other one, but the lightning hit the shorter tower. Why? How can it happen? The taller tower which was in the way, it was not hit, but it hit the shorter tower. Here we have got the answer for that. Now, P2 represents the shorter tower, P1 represents the taller tower. So obviously, the lower current obviously has to go in some direction other than P0, P1. So it will travel in the direction of the lowest electrical strength of the air, which might be like this. It might be like something else also like this. Might be going like this also. Here I am tempted to recall that if you have seen photos of lightning in the internet, there are hundreds of photographs in which lightning stroke, for example, from a point P0, traverses horizontally for several kilometers, comes back for several kilometers and hits the object somewhere here. Such things also happen. As I explained to you a little earlier, many phenomena regarding the development of the forward stroke appears highly unexplainable because the propagation depends upon the weakest electrical strength path. So leader will take a path of the weakest electrical strength and travel in that direction. So if it goes further for about even 10 kilometers, we should not be surprised. If we know the basic physics behind it, we will not be surprised. But otherwise, it can be a very, very big surprise indeed. The surprise will be bigger than the 10 kilometers or 20 kilometers horizontal traverse. So now I will repeat. From point P0, if the current is having a striking distance of D1 or greater, which is the distance from P0 to P1, then it will strike point P1. If, on the other hand, if the current is less than this value Is, then it will traverse in any other direction in which the electrical strength of the air is weaker, so it will traverse elsewhere, and it can in fact hit a short tower as has been made out by two gentlemen in the previous webinar. I'm very happy that they raised that question. In fact, I have faced this type of question in many lectures which I gave on lightning in the Power System Training Institute. For more than 30 years, I gave annually lectures on lightning and then insulation coordination for power systems. And this question has come up fairly frequently. How does it hit a shorter object than a taller object? This is the explanation for that. Now let's go further, see how to use it. We know the principle, how it develops based on the concept of striking distance. Let's see how to use it. This is what we have been discussing all the while. Let me move further. Now, the important conclusion one can draw is that if we design a system for 5 kiloamperes, the lowest current, then it's safe for all the other currents also, because it's a lower current stroke which can always play a trick, avoid the tallest object, come and hit the shorter objects. Therefore, if we design the system for 5 kiloamperes, then we have designed it also for the higher currents. Okay, now let's go further. Now again, we use the rolling sphere. We sort of think of the principle of the rolling sphere technique for practical application. So again, we have seen here that the leader has come down, of course, in a rugged path to point P1. Let's say that because of the specific prospective current in the stroke, the striking distance or the next step distance is Rs. So as I've been telling you several times, the leader can develop in any direction onto this spherical surface at all the same distance. It has got a capacity to hit this distance because of the prospective current magnitude in this stroke. Now, obviously, it cannot go upward again. It has to come essentially downwards. It may be sometimes like this and then come down like this. It can go like this, not so much, like this, and then come down like this. Or as I mentioned to you a little while ago, it can go on traveling like this and come back like this also. So right now, where can it go into the next step? Obviously, the striking distance or the next step distance is Rs for the prospective current I in that particular stroke. So it can terminate on any point on this spherical surface essentially we'll took of the downward point. So now this sphere tells us the region where the lightning is likely to strike. So this principle can be used to protect buildings, and therefore we will see that we'll use this sphere to roll around the building to be protected, as we'll see a little later. So we call this technique as the rolling sphere technique. So now what's the principle? Basically, we'll assume that we want to give protection down to 5 kiloamperes. For 5 kiloamperes, what is the striking distance? We have seen in the previous table. For 5 kiloamperes, using that particular equation, the next step distance is 26 meters. Or people have used 25 meters as a rounded off figure. If you want to play even safe, use 20 meters. So let us say that we use a sphere of radius 25 meters as the spherical surface onto which the stroke of 5 kiloamperes can go and hit. So now, so here, so if I use a sphere of radius 25 meters, the 5 kiloampere stroke will come onto any point on this spherical surface. So now, supposing I have got a tall building, I want to protect it down to 5 kiloamperes, So now, for the 5 kiloampere stroke, which I would like to consider very safe for the building, the striking distance is 25 meters. So now, okay, before I go further, I would like to mention one thing. I mentioned this earlier also. If the building height is approximately less than 30 meters or less than about 100 feet, geometric method is quite directly applicable. You don't have to worry about the rolling sphere technique. Now, to give an example, I have a small figure here. A building here which measures approximately 20 meters length like this, height approximately 16 meters, all arbitrarily taken. On top of this, I would like to provide a Franklin rod approximately 2 meters height, lightning rod 2 meters height. So how do I design the number of Franklin rods and their locations? The first thing I must always note is that the sharper the point, the more attractive it is for the lightning to come and strike. Therefore, first thing will be have a rod at the corners and along the edges, this corner and this corner. So where to put along the edges? Now, so I will put here this rod 2 meters height. From the table 2 of IEC, as I have shown you earlier, the productive angle is 70 degrees. So I draw a cone of 70 degrees. So the area of this radius is protected by this rod. So now, this corner, I've got another rod of 2 meters height. So this will protect an area of this radius. So now you'll see that this area and this area are protected. But you have got this area which is not protected. So I provide one more rod here, same 2 meters height, 70 degrees angle. You will see that the two protected areas are overlapping. So there's a safer thing. Now the other interesting thing is that now consider this height. This rod is effectively at a height of 16 meters plus 2 meters above ground. 16 meters is the height of the building plus another 2 meters. Corresponding to that 18 meters, you will find that the productive angle is approximately 20 degrees. So you will see that the cone of semi-conical angle 20 degrees is to be used for finding out the area which is protected. Now, if you do that, I've drawn here circles of these ones, circles of radius, of corresponding to semi-conical angle of 70 degrees, one, another at this corner, another at this corner, one more at this corner, and corresponding to the central rods, one circle here, another circle here. So you'll find that areas covered by the circles C1, C2, C3, C4, C5, 6. Totally 6 circles are given by this circle, this circle, this circle, this circle, this circle, and this circle. So now you'll find that they are overlapping, but only two small areas are not protected according to the geometric method. But personally, I would feel that they get protected because the areas are very small compared to the spheres. Now outside, external to the building, these are the circles of semiconical angle corresponding to the semiconical angle of 20 degrees. We'll see that even though the height is very large, the circle radii at the bottom, at the ground level, is very small. So it corresponds to only this radius from this ground point. So now this is how we apply the geometric method. Earlier I was discussing the rolling sphere technique, but I have jumped onto this application of the geometric method. Let us see now how to apply to the rolling sphere technique for a very tall building. The principle is the same, but instead of depending upon the geometric angle of 30 degrees or 70 degrees or 20 degrees, whatever it is, I roll this sphere all along the surface that needs to be protected. I will repeat it. It's worth repeating it. These are all discussed already. I have given the details, put it in writing. I have been talking about this all the while. 20 degrees protecting angle for areas within, protective angle of 70 degrees for top of the area, 20 degrees for the bottom area. I have been talking about that only. So now 6 areas. Okay, this is discussed. So now before coming to the rolling sphere technique proper, before going to the rolling sphere technique proper, supposing there are very large area building, the top area is very large. How can you apply the Franklin technique or the simply the geometric method? Now, even if you think of Franklin rods of great height, the whole area will not be protected. Therefore, what is done commonly is on top of this building, on this broad area, we provide a mesh made up of copper strips having a spacing of, for example, 5 meters by 5 meters. If you want to have a higher degree of protection, 10 meters by 10 meters for a different degree of protection, like that. So this is the mesh method. I'll come back to this a little later. Now I'll coming back to, I'm sorry, I'm mixing up geometric method, mesh method. I mixed up these two before rolling sphere because I wanted to emphasize to you that mesh method is a very important issue to be considered in parallel with the Franklin rod or even the rolling sphere technique, because in case of very large areas, this is a very essential principle to be adopted. There's the use of meshes for protection. So now we will go on to the rolling sphere technique. Now, as I told you earlier, for best protection, consider striking distance for the lowest current, typically 5 kiloamperes. For 5 kiloamperes, in the table I gave you earlier, for constants 10 and 0.6, the value came as 26 meters. So round it off 25 meters, that's safer. Or if you want to be still safer, use 20 meters as the conical area. Now this is only for air termination system design. For production systems, we have to consider in a different way altogether. That's the production system within the building, how to protect the electronics, electricals, etc. There's the system, productive system. But the production of the outside, external area of the external surface of the building. Now, as we said, we will consider the best possible level of production, considering 5 kiloamperes, for which the rolling sphere is having a radius of 25 meters. So now roll a sphere of radius 25 meters all over the top surface of the building to be protected. Let me repeat, roll a sphere of radius 25 meters all over the top surface of building to be protected. Why only top surface? It's a very interesting question. If you have got very tall buildings, much more than 60 meters, that means 200 feet, the lightning can hit the sides also, as we'll see a little later. It can hit the sides also. They are known as side flashes. Now, to prevent side flashes, we have to take small other step. We'll see that a little later. But for the moment, we'll consider the top surface only. So now, once you roll the sphere on the top surface completely, this rolling sphere, when it's rolling all over the top surface, it must contact either the protective rods or the mesh, or the rods must be located to avoid contact with the unprotected area of the building. Now, this is the basic principle. The sphere is rolled on the top surface. Now, our job is to see that the protective rods, the lightning rods or the Franklin rods must be so located that the rolling sphere must touch the tips of the rods and not touch the area of the building, top area of the building. That is how we have to choose the location of the rods. I will repeat it. Roll the surface on the top, roll the rolling sphere on top of the building, and see that rods are located such as the sphere will touch on the tips of the rods, but should not touch any of the areas directly. Now, supposing, as I told you in the earlier case, it's a very, very broad area. How many rods will be required? It will be a huge number. Therefore, what we do is, in addition to the rods which are located using the rolling sphere technique, we use a mesh also. Please remember the statement I made a little earlier. We have to use geometric method plus mesh method, or the electrogeometric method and the mesh method combinedly. This is obviously the most workable solution for lightning protection of the buildings from the external side. Internal systems, I will not worry about that in this set of webinars. So now I will repeat it. Work out the location of the rods so that the rolling sphere does not contact top surface of the building. It must contact the protective rods or the mesh, or the rods must be located to avoid contact the unprotected area of the building. I've shown clearly a simple principle, just to an illustration. This is the rolling sphere of the diameter 25 kilometers. There's one location of the sphere. I have rolled it further. You'll see that if this rod is not there, it will touch the contact, it will come into contact with the surface. That means lightning can get here, it can hit here. Therefore, I locate one more rod here. So now this rolling sphere rests on these tips of these two buildings. Similarly, between the next corner, I need one more rod here. So the rolling sphere takes on this position. So therefore, when the sphere is rolled on the surface, it will not touch the surface at all, but it will contact only the tips of the rods, lightning rods, or the Franklin rods. That's the basic principle of the rolling sphere technique. This is not to scale, but the principle is very important. I will repeat it. The current, the lowest that is seen is about 5 kiloamperes, for which the striking distance is 20, taken as 25 kilometers to be safer than 26, or even 20 meters if you feel they would like to be safer. Okay. Then roll the sphere of radius 25 mm all over the top surface of the building to be protected. Work out the location of the rods so that the rolling sphere does not come into contact with the top surface of the building. It must contact either the tips of the protective rods or the mesh, or the rods must be so located as to avoid contact with the unprotected area of the building. Now, again, I'm repeating this. No need to roll the sphere on the side surfaces if the height is less than 60 meters. So in such a case, side flashes practically are not seen at all. Therefore, there is no need to give protection on the side surfaces of the buildings which are less than 6 meters tall. Side flashes, on the contrary, are known to occur only on buildings which are more than 60 meters high. Even then, is very important. Experience says strike is limited to only top 20% of the height. This is a very important parameter. Even then, experience says the strike is limited to top 20% of the height. This area is to be covered with mesh, not the broad meshes, but closer meshes, or even in principle a sheet, a metal sheet itself. Okay. Now the above covers only the basic principles. For detailed practical applications, very exhaustive practical guidance and applications, we have to see, as I've been telling you several times, IEC standard 62305 or BAS 62305. Also for broad areas, in addition to all the rods, a mesh type protection is essential. We have seen this figure already. Height is less than 60 meters, no side flashes. Now this is a photograph reproduced from IC standards part 3, 62305 part 3. Now here you'll see that if the height is less than 60 meters, it's rolled on the top surface. The rolling sphere is rolled only on the top surface. So we'll see that this will contact the top surface entirely for this building, but it will contact only one side of this sloping roof here, and then subsequently it contacts only the ground. So it's three rolled positions of the sphere, showing where it makes contact with these two tall buildings. So here I have to have either rods at the corners to see that the rolling sphere does not contact the surface, or rods plus mesh if required. That means if the area is very broad, mesh also. Here again, you'll see that this area of the sloping area of this building needs no protection at all, whereas this area positively needs protection. Inside, of course, you don't have to worry. Now, supposing the building is taller than 60 meters, as shown in the figure B, roll the sphere completely on all the surfaces, but you'll find that we need a lighting protection system that on the top area, for which you can use either the geometric method or the electrogeometric method, as the case may be. And the side, rotate it, roll it rather, only to a height of about 20% of the height. That means about, if the height is only 100 meters, down to about 20 meters here. So this much needs protection. So this much will be mesh or sheet or closely spaced mesh. Think the broad meshes, as I mentioned, 5 meters by 5 meters or 10 meters by 10 meters, certainly will not give the required level of protection. So this is the principle of rolling sphere technique. Now, I have given here 3 photographs in which side flashes occurred. You find that this is a Washington monument where one of the leaders has branched and hit the top of the building, top of the Washington monument. But the main stroke has occurred the side here. And this again, you will see that this very tall building, the stroke has come and hit the side flash, hit the side surface of the building, that too at a corner. Obviously, corners and edges are very sharp. Therefore, streamers develop very quickly, very much earlier there than all other regions. Therefore, they need the most important consideration in designing lightning protection. See, it is the corner here. You see here the damage caused by a side flash, extensive damage caused by a side flash. The lighting is not if lighting protection is not provided, we must be prepared to face such an extensive damage. Oh, it's already 12 o'clock. We have been discussing, from the above 6 and 7, it is evident that a rod plus mesh system can be worked out for any building of any complex shape. For complex shapes, as I shown here, for example, a staircase room projecting on top of the top surface, or any other small projection, a room there on top, housing electrical machines or whatever, then additionally top surface of the projection must be provided with a necessary number of rods. Maybe a single rod may be enough, because remember it's already on top of a flat surface. Therefore, critical angle, the geometric method can be applied relatively easily. Not almost, not always, but most of the times, because these projections are relatively small in area, geometric method can be applied. If that is also very big, then of course we have to think of rolling sphere technique, but that's the very, very unusual case. But rod plus mesh technique on the whole is very essential, and it can cover practically all simple, complex, extremely complex cases. Now, I would like to repeat that I have mentioned it several times. One of the basic principles which can be applied to all situations are discussed here. The basic principles are discussed here. Detailed application procedures, guidances are provided in the standards which I have quoted several times. Now, one very special case is that there may be relatively small buildings which house dangerous, that means ignitable material such as petrol, fuel, ammunition, oil, etc. In such cases, the production system has to be what we call an isolated external system. For example, in figure 10, it shows that, let me say that this is the building where ammunition is stored or petrol is stored. Therefore, a strike to the building is not at all desirable. As I mentioned to you several times, all these methods are based on statistical experiences, field experiences which are statistical. Whether it's the geometric method or the rolling sphere technique, they are dependent upon field experience. In the case of rolling sphere technique, it's a striking distance concept where the constants K and N of that equation, if you remember, is subject to large variations. Therefore, we cannot say it's absolutely 100+% foolproof. We cannot say that. So we have got some things which are essentially very, very dangerous to be protected, so that no chance of lightning failure can occur there. We have to provide an isolated system. So there are two metal poles, one here, one to the other one. I have shown only two here. If the area is broad, it may need a set of such rods all along the length, also behind, front, everywhere. And then this is the most important part. There's a catenary wire which is hung between these two poles. So no strike can occur in the middle also. Typically, these wires or catenary wires also can be shown to have a protective angle of about 30 degrees only. Have been shown by field experience that their protective angle is 30 degrees. Most of the cases. But as I said, if the area of this is very broad, then additional rods, additional poles like this, isolated poles like this, additional catenary wires are required. Now, one question might arise. Can we mount these rods, whether it's the geometric method or the electrogeometric method? We have got rods and meshes. Can the rods be located directly on the surface? That's a very common question. But there may be cases where, because of certain additional safety conditions, they have to be isolated from the top surface of the building by a small distance. These distances can be worked out using the guidelines provided by the standards ISO 62305. I'll not go into those details because they are quite involved. There are several parameters to be considered there. So I would request the audience to consult the standards in case they need. Now, having discussed the air terminal system at fairly good length, we come to the down conductor system. I would probably mention at this juncture that the total lightning protection system for a building consists of three components. I have made out this point earlier also. The air terminal system, which attracts the lightning to itself. The down conductor system, which takes the current from the air terminals to the earth. And then the earth system, where the system distributes the current in the earth in a very safe way. That's very important, very safe way. Of this whole lot, the air terminal is the easiest to design. And then the earth system is the next easiest. The down conductor system can be very complex. Now, I'll have to emphasize again, it's absolutely compelling to have a down conductor system because the lightning current has to be taken down very safely. Otherwise, supposing lightning is attracted to the top of the rod and then the current flows through the building, then it's a disaster invited. It's a disaster invited. Let me repeat once again, it's a disaster invited. Therefore, to avoid this, we have provided the lightning terminal. That lightning terminal must be connected through a down conductor to the earth system so that the lightning current flows very safely. All through the principle of protection against lightning is that provide a convenient, safe path for the lightning current to go to ground, because lightning will ultimately always go to ground. That's where the negative charges are, positive charges are induced by the cloud. So this current which is negative flows into ground, neutralizes these negative charges, positive charges induced on the earth surface, as was discussed in the first webinar itself. So this is unavoidable. Lightning current must enter the ground. So now, if we avoid a safe path, we have done our duty. We have met our target. So it's absolutely compelling to have a down conductor. What's the purpose? To carry the lightning current down and transfer it safely to the earthing system. Now, down conductors are bonded to the aerial terminals at the bottom or to the mesh and come down to the earthing system. Now, I must again mention here, all the corners must be provided with lightning rods. Along the edges also, presence of lightning rods may be necessary, may be essential. Now, all these bottoms of the aerial terminals must be bonded together. This is a very, very important consideration. All these are to be bonded together by a metallic strip that will go along the corner of the building. Now, this will help the current to distribute all over this length of the bonding conductor, which is a very important parameter for ensuring the safety. Now, in principle, suppose you have got a 200 kiloamperes current stroke. What's the minimum area required for the conductor? Now, if you ask me, I can say that if you have got a 6 millimeter diameter copper conductor, it's enough. It will pass the current. The momentary temperature rise will be approximately 300 or 350 degrees centigrade. Within a matter of half a minute, it will cool down. But is it safe? 350 degrees. Is it safe? It is not. Therefore, the conductor cross-section must be sufficient. There's a very minor thing. Mechanical strength becomes the dictating part very, very often. So in principle, it's only a principle. Single conductor can also be used. But remember, we have discussed the dangers of a single tall conductor in the second webinar. The contact potentials will be huge, hundreds of kilovolts. The ground potentials can be huge, tens or even hundreds of kilovolts. Therefore, the current that can enter a person who is in the proximity can go from right up to 1000 kiloamperes to hundreds of amperes. So it can be extremely dangerous. So a single down conductor is a no. It's a no. Let me repeat. It's a no. Single conductor is a single down conductor is a no. Therefore, absolute minimum is 2, but even that is not at all advisable. At least 4 conductors would be better. 4 conductors, for example, at the 4 corners of a building. Even though rod may be 1 at the top, but 4 down conductors at the 4 corners will be very desirable. Very, very desirable. Not simply very desirable, but very, very desirable. Because the current will divide into 4 paths. And the current in each down conductor will be 1/4 of the stroke current. If it's at 200 kiloamperes, it will be 50 kiloamperes. Even that is dangerous. So the immediate moral is that nobody should touch the down conductor. They think it's a metal. Therefore, the resistance is very small. So voltage drop is very small. This is the common understanding. But this common understanding is totally wrong, as we have discussed when we discussed the tall pole, the inductance, the surge impedance of these conductors become the prominent factors, and that produces high contact potentials, high ground potentials, which can be very dangerous. Even 50 kiloamperes as told, if you have got only 4 conductors, 50 kiloamperes in each for the worst case is still very dangerous, very, very dangerous, both for contact and for the proximity. Proximity is even more dangerous because people can think, I'm not touching the conductor, therefore I'm safe. There's again a wrong notion. It's an illusion. So in real life practice, there'll be many air terminals. One down conductor for each air terminal is very desirable. Now, as I told you, if safety considerations require, it may be necessary to have more down conductors than the number of Franklin rods also. But this usually unusual. It's rather, it's rather unusual. But one has to think of these things also. As I told you, corners and edges are the most likely points. Now, as the bottoms of air terminals are bonded, lightning current will flow along the bonded conductor and distribute between all down conductors. I am repeating this. Every down conductor will therefore carry approximately 1 by n of the stroke current, lightning current IL, that's equal to ID. ID is the current in each down conductor. So this will correspondingly reduce the potential that a person would experience on contact. Risk reduced. It may not be zero. It may not be just a few percent, but it can be significant. One has to estimate that. So it should be the practice to avoid proximity also. Because as I told you, if you think of the worst case, 200 kiloamperes, these things can be very, very bad. So now, as I told you several times, the design and installation of down conductors can be very simple or very, very complex. Depends upon how is the external surface of the building. It's simply a rectangular surface, 4 surfaces or 6 surfaces. Easy to take the down conductor straight down. But usually buildings are not so simple in construction. There will be projections. There will be concrete blocks projecting, maybe for housing some things, or maybe rain protection, what we call sejas in our country, concrete projections. And then the other possibility is reinforcement bars inside the concrete pillars can be used as down conductors, subject to very direct approach. You see, this not necessarily mean a straight line approach. It's a direct approach, means the rod concrete bar, that's the reinforcement bars, must be having metallic continuity. If there is a joint, there are strict guidelines in the IEC BIS standards, the overlap of some minimum distance properly welded between them so that the current transfer from one rod to the other is absolutely perfect. So as I told you earlier again, the additional conditions and guidances are given in IEC 2305. Please go through that if you are trying to study how to design the system yourself. Now, sometimes if the down conductors have to be isolated from the walls to avoid current flowing through the concrete, then the isolation has to be insulated isolation. And these also must be barricaded so that no person comes into contact with externally. So many, many aspects need consideration in the design of down conductor system. As I mentioned a little earlier, the down conductor design is the most complex in many, many cases. Now, the next important thing is the down conductor, let's say, has brought the lightning current down to the earth level. Now it has to be transferred to the earth in a very, very safe way and distributed very safe way. Both are very, very important. Now, one small point which I have missed mentioning here is that now to study the effectiveness of the earth resistance, there must be a joint between the down conductor and the earth system, which can be separated to measure the earth resistance independently. This is a very important point, which I will mention. I will try to remember and mention it once again. Now, the earthing system is very obvious. The earthing system must dissipate and distribute the lightning current. Dissipate and distribute, both are very important. If there is no bonding between the earth end, it will still dissipate, but it will not distribute between the whole area. Therefore, both are very important. This usually consists of earthing system consists of rods or tubes driven into grounds, typically maybe 3 meters or 4 meters. There are again standards for that. One per down conductor is essential. Say every 3 meters or more. There can be horizontal rods or tubes also which can be used, but most commonly rods are used, not necessarily tubes. But driven conductors are typically tubes. They are more convenient because they can offer a large cross section. Rods are relatively easy on the horizontal side. Now, very, very desirable. Let me emphasize, very, very desirable. A conductor, usually termed a ring conductor, bonds the driven rods at the bottom in a ring. So it's called a ring conductor. Could be about 1 meter below the soil surface. It bonds the bottom ends of all the down conductors, forming a conducting ring. The function of this is very obvious. The current distributes all along this ring, and then therefore the current density, please remember the current density of the current when it enters the ground is very small comparatively. Now to see a simple example, consider a building of 20 meters by 40 meters. The perimeter is 20 plus 40 into 2, 120 meters. Simplistically, the above is equivalent to a hemisphere of radius A, that's 120 divided by 2 pi. That means approximately 19 to 20 meters. So it's equivalent to a hemispherical ring or a hemisphere of radius 20 meters. We have reproduced here the tables 2 and 3 of webinar 2, where we have estimated the step voltages for a current of for various currents right from 5 kiloamperes to 200 kiloamperes at various distances. Now, if you consider 5 kiloamperes at a distance of 1 meter, this is for a step spacing of 1 meter, and then soil resistivity of 50 ohms meter, which is considered a very good soil most of the times. If there's a garden soil, it may be 1 to 10 ohms per meter, but normally for all other soils, 50 ohms per meter is a acceptable figure. Now the step voltage here you see for 5 kA at 1 meter distance is 27.9 kV for R equal to 1 meter. Similarly, if you think of 20 meters diameter, the step voltage becomes only 0.07 kV. That means 70 volts. If you consider, for example, 40 kiloamperes, which happens to be the sort of 50% probability current. Now, probabilistic distribution of currents is a very important parameter to be looking at. If you look at these such figures which are available in literature quite a bit, 40 kiloamperes or higher has got 50% probability. So you will see that the step voltage is 0.56 kV, that means 560 volts, which is again quite small. But for 200 kV, again 2.75 kV, which may be still thought of as safe. So if you think of this ring conductor as equivalent to a radius, hemispherical radius of 20 meters, you will find that these step voltages are all pretty safe. I will repeat it. If you have a ring conductor bonding all the down conductors at the ground end, the building being 20 meters by 40 meters, the perimeter is 120 meters. If we equate it to a hemisphere of radius 20 meters, the step voltages are given by this. This is a very illustrative example. It is not far from the truth, but not exact. That's all I can say, but pretty close to real life. Now the currents, body currents, supposing the person has about zero resistance of the body, the currents, if you see here again, you'll find that if the radius of the hemisphere is only 1 meter, the currents can be 150 amperes for 5 kiloamperes stroke current. For 40 kiloamperes, that's the mean 50% probability lightning stroke. The step current can be 1200 amperes. If you consider 200 kiloamperes, the body current can be 6000 amperes if we think of this hemisphere of radius 1 meter. Now, supposing you think of the hemisphere of radius 20 meters, as we have seen in our present example, the body current can be 0.375 amperes for 5 kiloamperes, for 3 amperes for 40 kiloamperes, and 15 amperes for 200 kiloamperes. So we'll see that these things become very safe if the equivalent radius of the ring conductor is about 20 meters. Now this example will greatly highlight the importance having a ring conductor all around the building, which bonds all the bottoms of the down conductors. I will repeat it. All the bottoms of the ground conductors are bonded by this ring conductor. In some cases, having a complete ring may not be practical. IC standards specify that a minimum of 80% of the periphery must be covered by this ring. So 20% exception is here and there, but at least 80% is what the standards say, because that's only to provide for any exceptional cases where a complete ring conductor is totally difficult. So now we have covered the air terminal and then the down conductors and then the earthing system. As I told you, design of the air terminal system is the simplest because the principles are easy to understand. Down conductors, earthing system, the principle is even more easy, but extremely difficult to incorporate because there are many practical considerations which may come in the way of making it ideal. That is why we had to take recourse to the standards which are based on extremely extensive, I'm using a double superlative, extremely extensive experience, field experience. So we must follow the standards very closely in all these things. It's a question of human safety. Now, we have come to the end of this first part, namely protection of the buildings involving involving air terminals, down conducts and earthing system, in considering only the principles and always recommending that gentlemen, please go through the standards for a safe and effective system. Now, apart from the humans and buildings, the other object which is very commonly hit by lightning is the power transmission towers. So now we will discuss very briefly lightning incidents on power transfer towers. Now, remember, transmission line towers and overhead ground conductors of transmission lines, transmission towers are necessarily very tall, very tall. They're metallic and for safety, there are large clearances around them so that it may behave like a tall object in the open area. Also, the tower top is relatively sharp, not in the normal sense. It's not sharp, conical sharp, but it's a very small area. For example, maybe 6 inches by 12 inches, whereas the tower bottom would be several meters by several meters. In that sense, it's a sharp top. Therefore, it's highly attractive for lightning stroke to occur. Now, the phase conductors have relatively small diameter. For example, if you think of a moose conductor, which is commonly used even up to 400 kV transmission level, 32 millimeters in diameter. It's a very small diameter. So if the single conductor is used, it can attract the lightning by itself unless protection is provided specifically for that. So to prevent the strokes, to the phase conductors, overhead ground wires are essential. They are provided. The protective angle of 30 degrees for normal heights and reducing to 20 degrees for taller heights, as before in the case of buildings, is adopted here also. Now, let us see the order of voltages that can get generated on transmission lines. Now, direct lightning strokes are very common, very common. Over voltages due to these lightning strokes are extremely high in magnitude. Now, the main point to be considered is the tower behaves as a short transmission line. From the top to bottom, it behaves as a very short transmission line. Therefore, we don't have to consider its resistance or even skin effect resistance or inductance. Equivalently, we can use the parameter, its surge impedance. Typically, the value for large towers is 100 to 150 ohms. The largest towers have got equivalent surge impedance of 100 ohms. Now, if I can mention, the surge impedance is given by root of L by C, where L is the inductance per unit length, C is the capacitance per unit length of these towers with respect to capacitance with respect to ground, inductance, of course, with respect to the magnetic field only. Therefore, the surge impedance has got very substantial values, 100 ohms to 150 ohms. The larger towers having 100 ohms, medium towers having 150 ohms. The overhead phase conductors of EHV lines, they are varying from 300 to 350 ohms. If you think of, for example, a 800 kV transmission line, it may be close to 300 ohms. If you think of a 220 kV or 400 kV transmission line, the surge impedance may be of the order of 350 ohms. Now, protection wires are overhead tower top to tower top, ground wires, they of course go in the form of a catenary. They maintain minimum distance between the ground wire and the phase wire, considering various safety considerations. Therefore, a stroke can occur to the tower top or the overhead ground wire. Typically, if it hits the center of the overhead ground wire, that's the most dangerous thing. Now if it hits there, again, the conductor is to be represented by its surge impedance. Since the overhead ground wires are single conductors, typically the surge impedance is 400 ohms. Now, now some information. Due to direct or indirect lightning strokes, lightning voltages can occur on transmission lines. Lightning is known to contribute approximately 50% or more of the system outages in EHV and EHV and UHV system. This is not IHV, this is EHV. Please note that EHV and UHV systems. EHV up to 200, up to and including 220 kV is 2HV, 400 kV and higher. That means 400 kV, 800 kV, 1200 kV are UHV systems. Now, in all these systems, at least 50% of the outages are known to be due to lightning. Lightning can generate voltage the order of few hundred kilowatts. If the current is very small, can generate tens of megawatts, as we'll see a little later. Obviously, because of the currents being a few kiloamperes right up to 200 kiloamperes. The current duration, time to front, maybe 1 to 10 microseconds. That means it reaches from 0 to peak in a time of the order of 1 to 10 microseconds. Time to tail, that means the time to die down to half the value after the peak. Typically, few tens to hundreds of microseconds. And as I told you, the distance between the overhead ground wire and the phase conductor is to be such that the stroke to the overhead ground wire should not cause a flashover from the overhead ground wire to the phase conductor itself. That means it actually becomes an invitation to lightning to the phase conductors. Now, you will see that as we go further, the line insulation, that's the line insulators, 220 kV or 400 kV, how is it to be designed? We'll see it later. Because this is very critical because that influences the transformer insulation, which means the entire power system. Now, lightning can be represented by its equivalent circuit, which is a current source in parallel with its surge impedance. I'll not go into great details. This is just for information. The object struck is represented by its own surge impedance because in our case now, we are considering power line transmission towers. We have to represent the object by its surge impedance. They not I have mentioned the values also already, 100 to 150 ohms for towers, 400 ohms for ground conductors, 300 to 350 ohms for phase conductors. Now, typically, the surge impedance of the lightning channel is of the order of 1,500 to 3,000 ohms, but very often 3,000 ohms is considered. So, lightning stroke is represented by its current magnitude. For example, 200 kA, it divides between its own surge impedance and the object surge impedance. That's how we calculate various parameters in the case of transmission lines. Now let's consider a simple case. Lightning has hit the tower top of a tower, no overhead ground wires anywhere, just a tower with the transmission line conductors strung by an insulator string. This may be a porcelain insulator string or a polymeric insulator string, whatever it is. It's insulated from the tower. Otherwise, this current will directly enter this phase conductor. So now, assume 40 kiloamperes. It has got a probability of 50% or more. Therefore, we'll consider 40 kiloamperes. Now, if the surge impedance is taken as 100 ohms, that's the lower end of the surge impedance of the tower, you will find that the tower voltage would be 440 kA multiplied by surge impedance 4,000 kilowatts or 4 million volts. The tower becomes a high voltage object at 4 million volts. The phase conductor is only at the system voltage. For example, if it is 220 kV, its phase conductor will be only about 180, 190 kV. So you will see here that compared to the tower potential of 4 million volts, the potential of the line conductor is very small. So the flashover occurs from the tower to the across the insulator, from the tower, that's this end, to the phase conductor. So the potential of the tower end becomes 4 megawatts here. Then that cause a potential difference of maybe 3.8 megavolts between the insulates between the top of the insulator string and the phase conductor. So it causes a flashover. We call this a back flashover. A strike occurring from a normally grounded object tower to the phase conductor. It's just the opposite of what we normally see. Flashover from the high voltage object to the grounded object. But here it is the normally grounded object which attains a high potential and causes a flashover to ground. So now you will see that 4 megavolts can cause a flashover here. So now for 100 kA, which is not very rare, the potential can be 10 megavolts. Remember the beginning, I mentioned it can be hundreds of kilovolts to tens of megavolts. You see here, if it's 200 kA, it becomes 20 megavolts. That's all. It's a very small voltage. It's not 20 billion volts. Let's consider on the other extreme. No ground wire. Therefore, the stroke has hit directly the middle of a phase conductor here. Middle of a phase conductor. Here the surge impedance of the line is to be considered. As I told you earlier, it's root of L by C. It's not the resistance or the inductance alone. It has to be surge impedance. Typically, for phase conductors, it's of the order of about 400 ohms for single conductors, 350 ohms for twin and multiple conductors. So if you consider a 40 kiloampere stroke, 50% probability value, it divides into two parts between these two sides of the phase conductor. So 20 kiloamperes in each direction. So now the potential developed here is the current 20 kiloamperes multiplied by surge impedance. You will see here again 40 kiloamperes becomes 20 kiloamperes. The surge impedance 350 ohms. It becomes 7 megavolts directly on the phase conductor. So if you allow it like this, it will go and hit the transformer. The transformer will be destroyed in practically no time. Therefore, we have to design this insulator string very, very carefully. Remember, this design is very, very critical. If this flashes over, that means the voltage across the line to ground it gets limited by this value. We'll come to this again once again later. Now, suppose we provide, knowing all this extremely high, unacceptably high values, we will provide a overhead ground conductor. So now what happens is that, suppose I consider a 40 kiloampere stroke to the ground conductor. It divides into two portions of 20 kiloamperes each on the two sides of the ground conductor. That 20 kiloamperes comes here, divides between the forward path of the ground conductor and the tower surge impedance here. That's a very big advantage for us. So now you will find that the current to the tower is given by surge impedance of the line divided by the sum of the surge impedance of the two objects. So that comes to 16 kiloamperes. So it gets reduced from 20 kiloamperes to 16 kiloamperes. So for 16 kiloamperes, for 100 ohm surge impedance, it gets reduced to 1.6 megavolts. So it gets reduced to 1.6 megavolts. So the big advantage of using the overhead ground wire is very, very obvious. It reduces the potential from 4 megavolts if there is no overhead ground wire. 4 megavolts would have come here. Now it has reduced to 1.6 megavolts. Now, suppose you have got very broad lines. For example, if you think of a 400 kV line or 800 kV line or 1200 kV line, they cannot be one above the other. Horizontal like this. The tower will be roughly of this shape. So we have to provide two overhead ground wires. Now here we use the for height less than 30 degrees, for height less than 30 meters, geometric method 30 degrees. For height greater than 30 meters, reduce this protective angle to 20 degrees. This angle we have discussed at length when considering single poles, also when considering Franklin rod design earlier. Same principle is applied here. If the height is more than 30 meters, this angle is 20 meters. Otherwise, it is 20 meters. So now, suppose the lightning were to strike here, it should be prevented from going here. Therefore, this conical angle must be less than this, protective angle from this. That's the basic, very simple principle. Either geometric or the electrogeometric model is applied here. Now, we have seen earlier that the voltage comes here to this point, travels here. This voltage appears across this insulated string. It can cause a flashover. If the voltage is high, it will possibly cause a flashover. So now, see now, the insulated string flashover. The flashover is typically occurring between what's called the corona control ring at the line end and the arcing horn at the ground end. This flashover. Now, to take a simple example, I have assumed that the voltage appearing from this end is 8 megavolts. We have seen these values are possible because 20 kiloamperes multiplied by 400 ohm surge impedance gives us 8 megawatts here. 8 megawatts is represented by this wave shape. Now it flashes over, typically flashes over around 2.5 megawatts for a certain transmission line voltage. For example, if you take by 220 kV line, 2.5 megawatts is a little too on the higher side. If it's a 400 kV line, 2.5 megawatts is acceptable. We'll see why. So now, the probability of the current we have seen is 40 Ka, 50% probability value. So 8 megawatts is too high. So the what we call the critical flashover level of the insulated string tends to travel to the power station along the line. It causes flashover the first insulated string. If it does not, the next one. If it does not, next one. Like that, there are a number of insulated strings in the way. One or the other of them will cause flashover. So the voltage that finally appears is equal to the 50% probable flashover level of the insulated strings. That's what we call the critical flashover voltage level. That gets reduced considerably. That's the voltage which comes across the transformers in power stations. Now, how to suppress that? How can you think of, for example, a 800 kV line starting 2.5 megawatts impulse? We provide lightning arresters which have got non-linear resistors inside. So when the voltage exceeds a certain level, the current starts flowing through the arrestor. Once the current flows through the arrestor, develops a certain voltage. The non-resistor has got very, very non-linear resistance. As the current increases, the voltage does not increase substantially. It remains almost constant in case of what we call metal oxide resistors or zinc oxide arrestors. So this gives us a very basic principle of lightning incidence on transmission lines, the very high voltage that are generated, how that's reduced. The first line of defense, please recall and remember, is the insulated string itself. If that flashes over at a lower voltage, that lower voltage travels to the transformer, it is safer. But if we make it too low, there will be too many flashovers. Lightning voltage in the beginning I mentioned cause about 50% of the outages. Now, if we reduce the insulation level of the insulated string, then the number of outages will be very few, very frequent, unacceptable. Therefore, there are balances to be maintained between all this. The surge arrestor reduces the voltage to highly acceptable levels. In fact, I may in passing mention, there was a time, for example, in the 1940s and 50s, we were finding it very difficult to find a good arrestor which can reduce the voltage to an acceptable level, acceptable to our transformers. Today, the situation has become just the topsy-turvy. Arrestors are available with extremely good protective levels. That means this voltage is very much low. I cannot design a transformer insulation to withstand just this much. If I do that, then it will degrade due to the normal working voltage itself and fail earlier. That's the topsy-turvy case. At one time, it was the arrestor which attracted a lot of attention for improvement. Today, transformer insulation is attracting improvement. So now, with this very short introduction, I will complete this webinar. I would like to thank you, every one of you, for your kind attention, and then hand you over to Mr. Gopakumar, who has given me this great opportunity. I am very thankful to him also.
Sir, thank you very much, sir. We have a lot of participants today, and we have a lot of questions. The first question, we had more than 100 participants today throughout.
Okay.
And the first question I will read out.
Okay.
If the shorter building falls within the cone of protection of taller building, will lightning travel in a different path or attack the taller building?
That depends upon the current magnitude. For lower current magnitudes, the short building will become more attractive because the leader will not be able to travel to the taller distance. The striking distance will be shorter than the distance. Then it will travel towards the shorter distance. I cannot say anything more than that because currents lower than 5K are very, very few in number, very, very few, less than 1% probability. So if the design takes care of 5 kiloamperes, then the short buildings are very safe, even down to 5 kiloamperes. That means we use a rolling sphere radius of 25 meters. The shorter buildings are protected by the taller buildings. I hope it answers your question.
Yes, thank you, sir. The next question is, for a sloped roof, by providing a vertical rod in the top of roof ridge, can we assure the sloped roof surface fully protected if within the protection angle?
Certainly,
or
certainly.
Horizontal, yes, or horizontal conductors to be run.
See, it's always very desirable to run a horizontal conductor along the edges of the buildings, maybe top ridge or the side edges. It's always very, very desirable because if there are smaller currents, it can hit the edges. It depends very much on the magnitude of the currents also. It's very much desirable to provide a conductor all along the edges.
Yeah. Thank you, sir. We have a somebody has raised the hand, Mr. Davis, SITR, Mr. AR Davis. You can unmute yourself and if you can ask the question, Mr. Davis, if you wish.
Okay. Thank you, Mr. Gopkumar, and thank you, Professor Saab. It was a very enlightening and insightful session.
Thank you very much. Thank you very much.
And I am Davis. I am a power system engineer, power electrical, and I am now into safety training. So it was quite interesting to have your vast experience with a field touch on that. So thank you very much. So
thank you very much. Welcome.
And yeah, you talked about air terminal, you talked about down conductor, you talked about earthing system. So it's all a ocean by itself, but then I am more interested in the transmission line part, what you addressed upon. So where you talked about critical flashover voltage, sir. So and then the transformer insulation, how it is getting affected, and the new generation of lightning arresters. So can you just brief about this critical flashover voltage? And I know the time will be very limited for this, but I would like to hear from you, and offline I will also would like to connect with you.
So you are most welcome to connect on the on the telephone lines also. But here I will try to give you a very brief brief answer to your question. Suppose I have got an insulator string or a rod gap, whatever it is. Say, let me say 1 meter gap. Supposing I apply a 200 kV impulse, it will not flash over. Okay. Suppose I make it 250 kV, not flash over. 300 kV, no flash over. I apply 10 impulses, it will not flash over. Suppose I go to 400 kV, only 1 out of some 10 applications may flash over. On the average, this is statistical behavior. So if I apply 10, 1 may flash over, the other 9 will not flash over. So we call that a 10% flashover level. Like that, suppose I go to 450 kV, you might find that 3 or 4 out of 10 might flash over. If 4 of them flash over consistently out of 10, we call that 40% flashover. Like that, you go slightly higher, maybe you may come to about 500 or 510 kV. You find that out of 10 impulses, 5 will consistently flash over. May not be 5 always, 4, 6, 5, like that. On the average, 5 out of 10. If you apply 100, maybe 50 will definitely flash over. So that's called a 50% flashover probability level. Or the critical flashover level is that one. So a critical flashover, what's the insulator string or a rod gap, is that voltage at which the flashover probability is 50%. Now, supposing you have got between the lightning's point struck by lightning and the station, let me say there are about 4 insulator strings. Now what happens is that if the first insulator string does not flash over because it's only 50% probability, it does not flash over, the second one may. the second also does not flash over, the third may. So the probability of flashover increases very much. And finally, what is left with is only 50% flashover voltage. At least 4 strings from the point struck to the transformer station. If there are at least 4 strings, then we can say with almost certainty that the voltage coming to the transformer terminal will be approximately equal to the 50% flashover level or the critical flashover voltage level of the insulated string. So this is how the insulated string has to be designed very carefully, because on this depends upon the transformer and the surge arrestor selection. I hope I have answered your question.
Yeah. Thank you, sir. Thank you very much for giving this insightful answer. And I have 2 more bullet points just to. So this earthing conductor and lightning, the down conductor. Now, is it to be separated or it should be connected to the grid? You also talked about ring conductor. So I think you explained that. And also one more question, the down conductor in a building, usually nowadays it is because architectural view, it is taken through the ducts where the cables are passed or some other water lines are passed. Is it safe to do this shortcut method of bringing down the down conductor in a 60 meter or 100 meter building inside the ducts? Yeah.
See, the answer is very ambiguous. It's safe and not safe. See, if it's inside a asbestos tube duct, water and moisture will stay inside. May not be water but moisture. It can get corroded. And if there is any damage to the down conductor, it will not be seen outside. So there's a risk involved in that. The second thing is, if it's protected, protection from what? From contact.
Right.
If it's a down conductor, suppose it's in touch with the tube. If it's non-metallic, it may be insulating to some extent. If it's metallic, of course, it's dangerous. It becomes a down conductor by itself. Of course, that's not a question at all. So like this, it's dangerous, not dangerous. Both are possible, but inside a tube is not very desirable.
Okay. Thank you, sir. Thank you. And that's lightning system conductors, earthing, and the grid. Can it be connected to the grid? Because many times my safety electrical session, this is one of the question comes up. I know as per the latest IS 3043, never it says to be separated. But if you can throw some light on that, because there's many questions comes from many engineers who are attending my session, but and I also sometimes do not have a proper answer to that. So thank you, sir.
You see, sorry, today I'm having a little bit of a throat problem.
I know, I understand. After a long session, I can understand that with your age.
See, in principle, it'll be, when you say grid, you will see the power station grid. Am I right?
Any substation for that matter, there is a neutral earthing, there is a lightning arrestor, and there is a grid earthing. Now, yeah,
there's a power station grid or substation grid or whatever it is, and the lightning current flowing through that. See, I have seen both practices are there. What happens that suppose is suppose the down conduct from a arrestor, for example, is slightly isolated and it goes into ground through the soil itself directly.
Okay.
Not in direct contact with the grid. The current still enter the soil and then get into the grid also. Only thing is the current distribution will become more. That means current density will become less.
Okay.
So now, but anyway, see, there's one small issue which must be very clearly realized. The soil is not a conductor in the true sense at all. Absolutely. So when we say the common question, question earlier was, when is ground a ground? A ground is a ground when the potential difference between any 2 points, irrespective of the current, the potential difference is 0. That means you apply only 1 volt, it can take hundreds of thousands of amperes. The resistance is 0. But it can never happen. As I have given in this table today also, the typical soil resistivity can vary from 1 to 10 ohms for garden soil, 10 ohm meters. For normal soil, what you can say is 50 to 100 ohms per meter. For rocky soil, it can go to hundreds to thousands and thousands of ohm meters. So it has got a very finite, significant resistivity. Therefore, a soil by itself is not a conductor at all. So a ground is not necessarily a ground in the truest sense. For example, if you see an electronic circuit, there they have got a copper foil which acts as the ground. Copper foil is highly conducting, therefore that acts as a highly conducting ground. But soil is not like that. So in many cases, you have got electric systems grounded, electronic systems grounded, lighting grounded. Many people thought, as it was the practice in the world, they thought they'll be separating lightning voltage and these things, but that's not true. Suppose lightning enters at one point, it creates potential differences in all radial distances, which has been worked out in the one of the earlier webinars. It depends upon the distance. Okay. So now, for example, if the 2 points, lightning stroke point and the power system point, or the power earthing point is about 10 meters, the potential difference can be 20 to 30 kV. Okay. So that can cause a flashover inside the electronics in that particular situation. So whereas if you bond it, the potential difference will be hardly in terms of volts, because the copper conductor will be there. It reduces it to very nominal voltage. So it's preferable to correct it. There may be some exceptionally special cases when they need to be grounded. Then what they do is they connect a copper rod discontinuous with a such device like a glowed star tube. Okay. So if the voltage exceeds a certain level, for example, 150 volts or 100 volts, then they spark over and bond together. Otherwise, they are separate.
Okay. Thank you, sir. I think it was quite a power system, electrical engineering, but I think it was very, very useful. But one small hypothetical, I know the Gopakumar must be asking me to come out of it, the questions. One hypothetical question for common understanding. If an aircraft strikes a lightning, is it safe because electronics are there inside, and how the equipotential is maintained because intra-cloud lightning. So I don't know whether time permits.
Please repeat.
Am I safe in an aircraft if I come across that lightning strike when there is a intra-cloud lightning happening?
See, there are several issues in this. Intra-cloud lightnings happen typically at a height of 2 to 5 kilometers, typically. Now, aircraft flight usually takes care of the thunderstorm weather, and it tries to avoid the lightning path at all. First one, this is the second issue. First is 2 to 5 kilometers lightning zone. Now, if you see the first webinar, the aircraft flight is typically in the third atmospheric layer, troposphere, stratosphere, then mesosphere, because their lightning possibility is zero. Only you see what we call the upper atmospheric lightning events like the elves, tendrils, or blue jets like that. They are very safe. But aircrafts can be struck by lightning. Extensive care is taken. In fact, I have set up a lightning test facility aided by Aeronautical Development Agency for their purposes, where the light combat aircraft has been very extensively tested. Various protective measures have been incorporated and their adequacy tested in the laboratory. I have done the tests myself from 1992 onwards. Okay. Even today, it's going on for aircrafts, helicopters, various components, not this or that. You know, there are many.
Thank you very much, sir. Thank you very much, sir. Thank you, Mr. Davis. Thank you for the questions. In the chat also, I've posted some pictures. Probably you can also refer to that.
Thank you.
We have a few more people.
Thank you very much. Thank you, sir. Thank you
very much. In the chat box, we can. We have some more questions. Sir, one interesting question: whether any sharp tip is required for an air termination rod?
A very good question. In fact, very, very good question. You see, many people think sharper the tip is, the better it is. It's not really true. It's not really true. The reason is very sharp tip has got very high electric field intensity under the approaching leader. The very high field causes local ionization surrounding it. When the local ionization is there, it will have both positive and negative charges. In the case of normal ground rod, the earth is positive. So what it will do is it will attract all the electrons, and there will be a small cloud of positive charges around the sharp point. So this behaves like an extended electrode of much larger diameter than the point itself. Please note this. This is a little difficult to understand. I will repeat it. The sharp point has got a very high electric field intensity. Because of that, there will be local ionization around the sharp point. The local ionization has got both positive and negative charges. That's the electrons and positive charges. Because the rod being positive connected to the earth, it attracts and absorbs the electrons, leaving a positive charge cloud around itself. That positive charge charge volume acts as an extension of the tip. Therefore, the electric field reduces there, the flashover probability reduces. That means it becomes less effective to attract the lightning. It's a very, very good question. I'm sorry whether I have answered it clearly enough to you, I don't know.
Yes, thank you very much, sir. Thanks. It's clear actually. Now we have two more people who have raised the hand. Mr. Amrit Nam, if you have any question, you can unmute yourself and ask the question to Professor. We are not audible. You have to unmute. You are unmuting.
Yeah, I'm here. Yeah. Got it. My question is in between, sir told about interconnecting the ground conductors. I mean the different earth bits, but he was mentioning on the bottom tip or it is on the top of the electrode.
The question is not clear to me. Can you kindly repeat it?
Okay. If you have, suppose if we have 4 down conductors and 4 electrodes, this interconnection between the electrodes at the ground, whether it is on top of the electrode or bottom of the electrode, because you said
the top of the down conductor, that's at the bottom of the air terminal, they must be bonded. And then at the ground end also, they must be bonded. This ring conductor is typically 0.5 to 1 meter below Earth's surface. Because that otherwise, if they are on the surface, it is subject to damage, subject to contact with the persons. So 0.5 meter to 1 meter below is relatively safer, and also damage probabilities are much less.
Okay. Thank you, Mr. Amit, for the question. Before going to the next question, I will read out a question from the chat box from Mr. Batula Nagaraju. Striking distance is 20 meter. Then what makes the building height to 60 meters with the side protection? How it's protecting side of 30 meter, 40 meter, and 50 meter?
You see, the question of side flash is a very difficult issue to answer. Now, experience says that very tall buildings, that's more than 60 meters high, more than 2 feet, 100 high, side flashes occur down to maximum down to 20% of the height. That means if it's a 200 feet high building, it can occur down to about 20%. The only answer that can be given is when the leader approaches, when the leader approaches from the cloud, the sharp edge at the top corner is definitely more attractive than the side. Therefore, the possibilities that will go there is much more than the probability of its coming down. If the probability coming down is very low, it may occur once in a way. See, the whole thing about lightning is statistical. All the quantifications are subject to statistical variations. Side flashes do occur only when the tall building is very tall. That means about 200 feet or more. That too, because the top edge is definitely more attractive, so they tend to go there. Only some go down below that. I don't know.
Yes, the same question again from Mr. James Kuti. What is the mathematical ground of 60 meter height? I hope probably your answer is clear to others. Also, Mr. Kailash Prasad also mentioned if the building height is more than 60 meters, vertical, whether side protection is required for vertical side as well. This is always a question for engineers, because in most of these days, the modern buildings, they have complete glass at the top of the building. And then this glass is fixed to an aluminum frame. And now how to protect the glass is a big question. In fact, it's not a question, it's a challenge which we face every day. Now, how to handle this, sir?
Okay. See, the 60 meters or 200 feet it has been brought out by field experience. Field experience. There is no mathematical proof for that. But what can be done in principle is that today computers are available, softwares are available. We can do the simulation and also find out what are the field intensities on the ground end of the such tall buildings. Also, it is possible, but it's extremely complex because the buildings have got a complex shape. You've got windows, aluminum frames, glass sheet. Inside the glass sheet, something else. The field computation is extremely complex, but field experience shows very clearly that side flashes are limited to only top 20%, not more at all. I've shown 3 photographs also there. Washington Monument, another building, and then one more building where the extensive damage has been shown. It is limited to top 20%. Even the windows, the problem is the top 20% to cover that. A welded mesh like thing structure would be very welcome. That can be enclosed in the plaster, cement plaster, or other than the buildings. But at the corner of the windows also, it's preferable to provide a welded mesh covering the entire window, or at least the top portion of the window. But people may think it is not really nice to look at. But safety is more important than the look, I think so. But I don't know what you say about that.
Yes. Yes. Safety is more important than appearance.
Yes.
So we have no compromise. But
Yes.
here the advantage is the current of these lightnings which is coming to the side of the building. These are always smaller currents. So
Smaller,
it cannot.
smaller currents.
Yeah.
Smaller currents.
The corners and edges has to be protected. That is more important. Also, if there are
Absolutely.
electronics installed, then those also require protection. So now we have Mr. Subba Reddy, sir. Mr. Subba Reddy,
Oh, yes.
can you unmute yourself and ask the question?
Yeah, thank you, Gopakumar. Good afternoon, Professor Nagabhushana. Subba Reddy here.
Good morning. How are you?
Fine, sir. Fine.
What question?
Gopakumar, thank you. Professor Nagabhushana was my mentor, guide, and the chair of the department. I am from the same high voltage department. Lot of things I have learned from him. Really, it's a good interaction today with all other people here. Sir, only 2 clarifications I do require. You said that soil is not basically not a conducting thing, but what we have read and we have encountered many of the cases that lightning striking at a far off distance could be 1 or 2 kilometers. There are cases where the induced voltages have disturbed many of the electronic equipments which have been damaged with the nearby, could be laboratories or many of the equipments which are prone for this induced voltages. That is one thing. And the second one is about the simulation. As you told, yes, we do a lot of simulations, but still, as you mentioned, the field experience is very, very important because in the simulation, some of the parameters or some of the things which we choose may not be the dynamically changing things. We do employ some statistic values where like if you say the surge impedance values, just we take it and we try to come out. But practically with the experience level, the information is much, much better. So the person who has the practical knowledge will be able to better interpret the results. That's what I felt.
Yeah, what you say is right. But regarding the first question, you see the danger of the electronics depends upon 2 things. One is if at all the ground potential comes into picture. That means if the electronics is grounded improperly, is subject to danger, but 20 meters away, the dangers are substantially reduced. The more important question you asked is, how does it get affected? It's due to the magnetic field inducing voltages inside the electronic system. If it is not properly magnetically shielded, the magnetic field due to lightning is known as LEMP, lightning electromagnetic pulse, that can induce voltage between the ground and the components of the system, and it may fail. In fact, this is a very serious question, particularly serious question. So proper protection must be provided in addition to proper shielding.
Yes, sir. They are also trying to use this what is known as SPDs. You know very well.
Oh yes.
So, yeah.
Oh, yes.
So these are to a certain extent they are able to protect, but there are many of the cases which have been reported very recently. Also, there are failures and a lot of electronics have gone bad. That is where I was thinking: is it because of the soil conductivity of the nearby lightning strike, or it is because of the individual electronics which they are due to the magnetic field or LMP, sir?
It's certainly
sir.
due to the induced field. Certainly due to the induced field.
Sir, with your permission, can I answer this question, sir?
Yeah, yeah.
This is
Sure.
yeah, sir. Okay. See, you are talking about the low voltage installations, I hope, and
Yeah,
electronics in the building, not related to the high voltage application. Am I correct?
yeah, yeah.
Actually, in the system earlier, we were thinking, you connect everything to the earth electrode in soil. This was never included or written in any of the standards. So the standards always had considered your earth is a protective conductor, which is a metallic busbar. You connect everything to the metallic busbar. Was the concept which was done even from the beginning until today in the standards. But somehow we have the habit of connecting electronics separately to a earth pit in soil, then different parts of the building to the separate earth pit, earth electrodes in soil, which is absolutely wrong. In this condition, even if you put an SPD is not going to work. Also, a lot of places, the more than the quality of the SPD, the method with which SPD is installed means with a long lead length, long wire length SPDs are installed. As a result, SPD's results are not encouraging. The electronics keep on failing. So hope my answer is clear, sir.
Yes.
Thank you. So can we go to the sir? You can add something, sir. Now, sir.
Yeah, thank you, sir.
Thank you, Subbareddy. Long time.
Yes, sir.
My student.
Thank you, sir.
So we have another question from Mr. Ranadeb Chandra. Mr. Chandra, if you are there, you can unmute yourself and speak. On the same time, I will answer one more point. Mr. Mainik Chatterjee has asked, one moment, please. Dr. Nagabhushana explained using the structural steel. Somebody asked whether in National Building Code allows this. Yes, NBC 2016 had included it in the standard. Over to you. Please ask the question.
Sir, I have a query regarding, suppose if there is any DG stack, and for DG stack, in order to ensure the appropriate lightning protection, what should be the system, and what should be the downcomer size, whether 1 or 2 lightning arresters or downcomer would be required, and how it would be connected to the ground, sir? You
see, it depends upon the correct locations of all the things. It will be very difficult to answer offline like this.
Suppose sir, it is a 30-meter height of DG stack. Say.
What is that? What is that?
DG stack.
Shall I answer
DG
that?
Stack. DG
shall
stack. Yeah,
I answer?
Yeah, please go ahead. Please go ahead.
I hope nowadays in data centers, especially data centers with a large number of data centers use large number of diesel generators, and since the space required to keep all of them are in the ground, so it is stacked. That means one above the other in a large metallic structure. So I hope that is the question, Mr. Chandra. Is it the understanding is correct?
No. My question is that suppose for a DG stack of height 30 meter, what should be the size of the downcomer and how it will be connected to the ground, and whether one lightning arrestor will be required or say,
no, that is the second part. The DG stack which you have mentioned is
DG stack height,
number of DGs.
No.
Which is
number of
DGs.
For number of DGs, there is a stack basically. One stack only. Is
yes, Gobagomar. He is talking about the exhaust pipe.
Okay, that is the exhaust pipe.
Okay. Yeah.
Okay. See, most of the time the exhaust pipe is not a standalone pipe. It consists of a metal structure as well. And basically this structure itself will do generally the structure is of higher size than what is recommended in the standards for the minimum down conductor thickness. The frame itself will do the job.
Correct.
Provided you have a better, longer rod at the top to avoid the direct strike at the edge of this particular chimney. But the chimney and the tower also has to be bonded.
Okay.
So I hope the answer is clear. So can we go to the next person?
Now the question and answer both are clear to me.
Thank you, sir. Thank you, sir. We have one more hand raised, Mr. Anandan. If you have the question, you can unmute yourself and ask. Also, Mr. Batula Nagaraju and Mr. Sanjay Kolatkar. If you have any question, please unmute yourself and ask. Mr. Nagaraju, please go ahead.
Good afternoon, Gokumar sir. Good afternoon, Nagabhushana sir. Sir, my question is regarding explosion areas, sir, where hazardous gases are present, sir. Yes, sir. Like a hydrogen gases, sir. In this area, which method is the best suitable method, sir? I want to hear from you, sir.
You see, hazardous gases, if they are present, there are very stringent specifications for that. What's the amount and how is it distributed? See, there's a very different situation altogether. Nearly 90% will not be enough. That will be purely secondary. Because the hazardous gas, if they are present, they are dangerous all the time, 24 hours a day. Hydrogen particularly is highly inflammable. Because in atmosphere, there's so much of oxygen and hydrogen, they interact, they can catch the flame anytime almost. Hydrogen is very dangerous that way.
Yes, sir. Yes, sir. I will quantify this one also, sir. It's around 30,000 kiloliters hydrogen gas, sir. It's present in during normal operation, sir. Generally, it's not a storage area, sir. It can be considered as a zone 1, sir, as per EC 60079, sir.
Okay. You see, one thing is certain. If the air terminal, down conductor, earth connections, they are all spark free. Totally spark free. That means absolutely metallically conducting. Then there should be no problem. You see, lightning strokes must occur to the air terminals. That must be made 100% sure. And then the down conductors, if they are very long, the bonding between portions of the down conduct must be very thoroughly bonded. And then ground conduct connections also must be very thoroughly made. Then there will be no chance of a spark at all. This is the most important part. There should be no spark, because the spark can ignite the gases and that can result in disasters.
Yes, sir. Yes, sir. Correct, sir. As you said, it's almost equipotential bonding, sir. Yes, sir. For connecting at field, various mechanical pipelines, instrumentation system, everything is going, sir. It's connecting also. We cannot ensure everywhere each and every metal part connected properly. That is also practically difficult in it, right, sir? Sir, my question is, sir, whether isolated lightning protection system is advisable or this equipotential bonding system is advisable.
So please repeat the last part. What
sir,
please?
Sir, actually, this is a very vast area, sir. Connecting all the vast area, very huge area, sir. Almost.
Okay.
For connecting this all the mechanical pipelines, metallic parts, towers, extraneous parts, all instrumentation pipelines, or all other systems interconnecting together with less contact resistance. Also, it's a very difficult, sir. Okay. Anyhow, we will try, sir. I just want
Mr. Nagaraju, we understood. I will just explain the question to Professor. Professor, the question is whether his application is for a larger area, whether isolated lightning protection is advisable or not. But before that, I would like to add one more point. Mr. Nagaraju, you told that it's very difficult to make connections with very good contact resistance. So this is an excuse which an engineer working in that particular field should not say. As an engineer working in this field, it is the duty of everybody who is working in the safety of that particular plant. They should ensure that all are interconnected properly as per the recommendation of the relevant standards, and you should ensure minimum contact resistances as per the recommendation. Because probably, if you think that it is difficult to make, and if we keep quiet, probably that becomes the reason for an accident. So, sir, the question is whether isolated lightning protection can be implemented.
It can be, But one thing is certain, as you said, safety first is the dictum always. More difficult, less difficult is not at all a question that should be raised. Safety first. So to ensure that safety, whatever is necessary must be done. There's no doubt about it.
Yes, sir. I'm not talking about installation, sir. Once we will install it, sir, ensuring each and every metal part maintenance also it's very difficult, sir.
Whatever it is, if safety is involved, maintenance precautions also must be taken into account. Now, as far as the lighting system is concerned, continuity, that means contact resistance must be as low as possible. Just the pure metal impedance or resistances must come into picture. If there is any chance of a spark, you know what is likely to happen. You know it better than anybody else because you are working in that area. The risk involved is also very great. The flame can spread over a huge area. Safety first, safety first, safety first.
Yes, sir. Yes, sir. Means isolated, sir. What is your opinion on isolated?
Isolated installation, isolated production system can be used, certainly used, but it has to cover that large area. So how many towers will be there, bonding them, cantilevers? It's like the product. Yeah, it can be done. Certainly, it can be done. And then if the area is huge, the ring conductor will be very huge, very large, maybe equivalent to about 100 meters diameter almost from what you say. I'm just guessing through my head. The current density will be very small, maybe not even a few kiloamperes will be there per meter width. Because if it's 200 kiloamperes, and if the distance, the length of the ring conductor is 200 meters, it's only 1 kiloampere per width of the conductor. It will be very safe.
Yes, sir. Yes, sir. Yes, sir. Correct, sir. One small final question, sir. Actually, this striking distance in explosive area, it will decrease, sir. Is it?
What's it? Please repeat.
Striking distance, sir. Actually, actually at the point of strike, lightning to that termination rod or catenary wire system, whatever it may be, there definitely spark we cannot avoid, sir. But these gases are continuously, it has a low density gases. It will starts continuously going up, sir. Whenever it is a leak.
Okay.
Yeah.
I understand your question. For example, hydrogen, the electric strength of pure air, that means without hydrogen, with hydrogen, they'll be different. So it may tend to go where hydrogen is more. Is that your question?
That is one matter, sir. And one more thing, that calculating with the rolling spear method or calculating with the protective angle method, that distance between the, suppose if it is isolated lightning protection, the distance between the point of strike to that protecting area, sir, where the tanks are present, whether we need to consider just normal as the rolling spear method or this protective angle method, or we need to take care any additional extra care for measuring the separation distance in the where
no. Okay. Now what you are saying is there's an isolated production system. The distance between that and the building protected is so much. Is that enough?
Yes, sir. With rolling sphere is enough, or any extra care to be taken?
For the clearances, rolling sphere is not required at all. That depends upon the rolling sphere or the geometric method is not applicable there at all. It's the clearance between a down conductor essentially and the area under protection and the volume under protection. So a rolling sphere or geometric method is not of relevance there at all. It's the clearance that's required.
Sir, I'm not worrying about the flow of current through down conductor, sir. I'm talking about only point of strike, sir.
Point of strike. What's the height of the tower, down aerial terminal?
Actually, that it is around 45 meters structure, sir, where hydrogen are present, sir. Its IBD, intra-barrigated distance, is around 30 meters, sir. What could be the approximate point of strike? We can put that 8 termination rods.
I think it would need a person-to-person discussion.
Yes, Mr. Sir, I would like to little bit interrupt in between. Mr. Nagaraju, what we can do is, if these specific questions are there, we can have an one-to-one discussion with Professor probably on any of the day, probably Monday, Tuesday or something like that. We can arrange it, not an issue.
Yes, sir.
Thank you.
Sir.
Thanks for the question. And we have Mr. Manik Chatterjee. Mainak Chatterjee, if you have any question, you can unmute yourself and speak. So please carry on.
Sir. Good afternoon, Gopal sir and Professor sir. Am I audible?
Yeah.
Yes.
Yeah.
Yes. Sir, actually, I am from Haldia, West Bengal. And the issue that, sir, I am working in a chemical factory. The plant is like 40 years old. We are producing sulfuric acid. And previously, there is a plant what used to produce the phosphoric acid over here. So the issue is that when we dig like 1.5 meter, 2 meters just, so for the longer period of time, those acids were ingressing and soil conductivity over here is huge high. So what happened this pre-monsoon season or the monsoon season, when we observe there is a lightning, means we heard the sound, we see the light, but it is not like just happening here. But we found some of our instruments what actually connected with plant structure, those instruments damaged. So actually, sir, we contacted some SPD vendors. They also came here to study and all those things. So what they are suggesting that as due to our soil is very conductive, so if lightning happened in certain distance, those lightning current propagate through the soil, and some of the times it came contact with our structures, and they are just damaging our system. So sir, please show us the path how we can means conduct a study and how we can protect our instrument electronic systems what actually situated in field.
I see. There are two issues. If the soil is more conductive, the potential differences are greatly reduced. So it will be less dangerous from that point of view. So the probably the difficulty you are facing is something slightly different. Must be due to the magnetic field of the current, not necessarily the potential differences on the ground. But it's difficult to directly decide that from here in this way. I think Mr. Gopkumar will agree, as I said a little while ago, one-to-one discussions would be very good. It's not merely SPD. It's not merely SPD. It's not merely soil resistance.
Okay.
It's a complex situation.
Yes, sir.
I don't know. Mr. Gopkumar, you agree with me?
Okay.
Yes, sir. Definitely. We can have a one-to-one discussion and explain these subjects very much.
Sir, how can I contact you, sir, means for that discussion?
Gopkumar is easily accessible.
Okay.
You can. I will put my email address in the chat box. You can note down, and you can probably, if you have received the email, you can reply back to that. Somehow it will come to me, or I will put my address in the chat box. You can write, and I will organize the meeting with the professor. Sure.
Yes.
Thank you.
Sure.
So we have some more questions.
Thank you very much.
It's already 1:20. We have to take up some more questions. Let me see some of the questions. So by the same time, if Mr. Davis, if you have any question, you raised your hand. If you have any question, please go ahead.
Yeah. Thank you, Mr. Gopkumar. I think there are many questions, and I think all of them are very, very valued questions. So from the hazard point of view, if I just want to add one point here, the bonding and earthing is the answer to the question the previous. I mean, this what my feeling, because earthing, if you do it properly, then it is a zero potential. And I think that's the answer. And as Professor Saab has said, you will connect one by one, one-to-one, and then answer it. So thank you, Gopal. Thank you.
Now, all I would like to say.
Thank you very much. Sir, go ahead, sir.
I have nothing to add here. There's somebody is asking a question.
No, actually, we have a lot of questions. In the next session, that is on next Sunday, again 11 o'clock, I think we have to answer all these questions. There are several. So it's difficult to.
What I find is this, many of the questions relate to practical situations which need individual study, particularly by professionals like you, rather than an academic man like me. Many of the questions are of that kind. For example, the chemical factory, that need a different kind of outlook. It's not merely the lighting system, it's something different. It's something in addition, not different, something in addition. Anyway, that's what I would like to say, that's all.
Thank you, sir. One question we will take. Sir, one question we will take. For a building protection, you mentioned that practice is to consider 25 meter striking distance equivalent to 5 kiloampere striking current.
Yeah.
How less than 5 kiloampere striking current is taken care? Are the currents less than 5 kiloampere not considered and harmful?
Yeah, that's a good question. So typically, the lowest current considered is 5 kiloamperes, but as low as 2 kiloamperes are also seen in the field. But the probability is not even 1%, 2 kiloamperes or less. So that's why people don't bother about that part. It's too low and protections required also would be too small. That's why people consider 5 kiloamperes as the sort of lower limit. As I told you, 5 kiloamperes is about 99% probability, if I remember the number right. So the lower currents are only 1% probability. And usually, as the currents are low, the dangers are also relatively very small, comparatively very small. But if they tend to be significant, then it needs to be considered. Then the striking distance has to be calculated using that equation 10 I to the power of 0.6. They use I as 2 kiloamperes, you will get slightly different number. 2 to the power of 0.6 is approximately 1.5. So it comes to about 15 meters diameter radial. That's the radius of the rolling sphere. 15 meters instead of 20 meters or 20 meters. That's why the standards are using 20 meters that may cover closer to about 2-3 kiloamperes also. That's it.
Yes, thank you. Thank you very much, sir.
Mr. Gopakumar.
Yeah.
Sanjay
Mr.
Kollar, sir.
Please.
Yeah. See, I have a couple of questions like in the hill, I stay in Pune, it's a hilly region nearby, and we are doing some resorts over there in the hilly region where there is a huge reservoir of backwater. Now the thing is, the resort is on the slope of the hill. So the fascia towards the reservoir is much higher than fascia on the opposite side. So one side of the being on the slope of the hill, one side of the building is has got a drop of around 15-20 meters, and other side the drop is hardly around 5 meters or so. So that makes everything very uneven for the from the lightning protection point of view and all that. So how to go, or what additional protection is required to be taken for the designing, or say for the installation of the lightning conductor, say increase the size on the higher side or decrease the size on the lower side. Secondly, the levels are very, very irregular. So what is happening is the water doesn't stay over there if when the earthing pits are made. So only in the at the time of the you can say the rainy season, there is a very good water accumulation in the ground, which very fast goes down and soil dries up, and that becomes a challenge to maintain the earthing results. So what can be done on that account, or can I take the lead of the down conductor directly to the reservoir and bury in the reservoir, which is around 100 meters away from the building compound?
Yes, sir. I would like to, sir, Nagabhushana, sir, with your permission, shall I answer this?
Please go ahead.
So,
please go ahead.
Mr. Sanjay, the question here is, number one, with your explanation, we may not be able to understand how the building looks like, number one. Number two, this lightning protection, of course, the recommended practice is to have a type B earth electrode. And if you go for a type B earth electrode, whatever the earth, the final result of this resistance, RE, earth electrode resistance, is a little bit immaterial. So go for a type B earth electrode. But if you can send the drawing, or if you wanted to have a discussion with professor, we can arrange a personal discussion and explain to you. Otherwise, it will be very difficult to answer the question. Thank you very much.
In fact,
can I draw the conductor directly till the reservoir to have a better grounding? Because there is ample of water.
That will be a big mistake. that will be a big mistake because
Okay.
lightning doesn't need water to dissipate.
Absolutely
And
right.
if you take a Yes, sir. If you take a longer conductor, actually you are inducing potential and you will have bigger failures in your electronics and shock.
Absolutely right. Absolutely right. See, there are two things. Pure water is highly resistive, anti-conductive. So it depends on if it's a fresh water from rain, it will not be conductive at all comparatively. Compared to soil, may be more resistant, more conductive than the water. So it's a very big question, and then it's not possible to give a simple answer. 2 into 2 equal to 4. Like that, it cannot. It's not be possible to give an answer. You have to study the variability of the soil resistance with the fresh water, with the non-fresh water, things like that. They are all becoming important. It's an extremely complex situation what you are having. As Gopkumar said,
I can have a
May I come
person
in?
to person discussion afterwards, I think.
May I come in for a minute if you allow, Gopkumar?
Yes,
Davis
please,
here.
Mr. Davis.
Yeah. So I come with a lot of 35 years of field experience. So I can add to what you are mentioning here. There are various types of customized earthing also possible. It's not that only 3-meter electrode depth is, you can also go up to 10 meter. And you can also go for rod earthing. And there are many solutions available customized to your resort hilly terrain requirements. So I think, I think you can connect later and then do that.
Thank you very much. Thank you very much.
Thank
But
you,
thank you very much. But please understand that there is nothing called this chemical earthing and all. People try to, fool, saying that there are chemicals available which will absorb all those things. Chemical earthing or this earth enhancing compound is recommended only above 3000 ohm meter, which is very clearly written in the IS IEC 62305. You can refer clause 5.4 with a picture. It's written. So there are several solutions available, as Mr. Davis explained, but never fall into this the word chemical earthing and all these tricky things. There is no trick for electrical safety. We have to follow the fundamentals. So
In fact, we had a
over to
debate
you,
in BIS meeting.
Nagabhushana sir.
yes, please.
Nagabhushana sir.
Yes, please. What is the question?
So in this case, shall we close for the day and continue with the questions, because it's almost 2.5 hours.
I must thank Mr. Gopakumar and everyone who has participated for in fact, it's a delightful experience for me. The questions are more important than the presentations. Thank you very much, one and all. Thank you very much.
Thank you.
Thank you very much, sir. Thank you very much. Now, gentlemen, we have the next session on coming Sunday. And the session is actually the fourth part of our this series of lectures, know all about lightning protection. The fourth session is about additional topics such as some glossary methods of protection, possible laboratory testing and limitations, then lightning and the power transmission lines. Pardon, sir?
Illusory techniques, not glass. Illusory techniques.
Yes, illusory techniques. Okay, I will also change in my wording. Thank you, sir. So, thanks for all the participants to patiently listen to us for almost 2.5 hours. We have so many questions. We will compile the questions for next week to answer properly. Thank you very much. By this, we will end up the program. Thank you very much, Nagabhushana sir.
Good day to all of you.
Thank you, sir.
Thank you.